Here we have an example 2, where we are given parts of information. Well, actually that's enough, we will see. So we have a linear transformation from R3 to R2. So this one transforms vectors with 3 components somehow into vectors with 2 components. Now, in this example, we do not know what is the linear transformation. What we are given in the problem is the images of the basis vectors under action of the linear transformation. So we will have some basis v1, v2, v3 for R3. So that's a basis that is not necessarily standard, it's some non-standard basis for R3. And what we are given here are the images of the basis vectors under the action of linear transformation T. So these here, these 3 vectors, 1, 0, 2, -1, and 4, 3, those are true vectors from R2. Those are not component. Those are not coordinates. Those are real vectors. Okay, so we need to see how all this will work. We are going to build the representation matrix, and then we are going to see how to use this, and we will see it's not that complicated. So, as usual, I just remind you what's the goal in general is to build the representation matrix for a linear transformation relative to the basis BV for the domain and BW for the codomain. So in our case is R3 and R2. So once we have built that representation matrix, we need to use it to find the image of some vector under the action of the linear transformation using the representation matrix. So that's the beauty of it. The important reminders are that the representation matrix works on the coordinates, and it's always relative and changes and depends on the basis we choose for the domain and the codomain. Each time a basis changes for domain or codomain, our representation matrix will change. So the representation matrix here, relative to the basis B and C, is always applied to coordinates of a vector in basis B. So we have a vector, but we need to find its coordinates in basis B, and then we do the product representation matrix times the coordinates of the vector in basis B. And as a result, we are going to get the coordinates in basis C of the image of Tx. So image of x under action of T. So what we get back is the coordinates in basis C. See, it says coordinates B for inputs, and the output are the coordinates in basis C. And then we just need to apply the definition of the coordinates and expand. So this is a general principle, and that's how we do it. In general, to build the representation matrix, in this case, in our problem is given, but in general, we would need to apply the linear transformation to the basis vectors of the domain of the input space. And what we get are the objects living in the codomain, so true objects, in our case true vectors. And then the last step is to find the coordinates of those objects, of those vectors, in the basis C of the codomain. And then once we find them, you just put them into a matrix in columns, and that's our representation matrix relative to basis B and C. So that's a general principle. So be careful. Representation matrix works on coordinates always, and it's defined and found by action of the linear application on the basis vectors of the domain, and then we proceed further. In general, if the basis for the domain is not specified in the problem, we are going to use the standard basis. And if the basis for the codomain is not specified, again, we are going to use the standard basis. So here is our linear transformation. It's a mysterious one. We don't even know how it looks like, what's the expression of it, we know nothing. All we know is what is the action What is the result of the action of the linear transformation, the mysterious linear transformation, on the basis vectors of the basis B from R3? So all we have is the images of the basis vectors of the basis B. So we are going to use basis B for R3. Okay, so these are the images, puff. Now, as you see here, there is no mention about the basis of R2, which means for R2, for the codomain, we are going to use the standard basis. You see, for R3, they said, oh, it's basis B of R3, and these are the vectors for the basis B. And their image under the action of the linear transformation is given here. Okay, fine. But they don't say anything about R2. What's the basis for R2? Well, it's standard basis. If it's not specified, it's always standard. Okay, so here for R3 is specified is basis B. For R2 is going to be standard. So, reminder, the linear application works on objects, and it was applied to the basis vectors V1, V2, V3 that are given here from the basis B. So these are the objects, the real true vectors from R3. We applied the linear transformation to them, and what we get is the image, which are the true vectors of R2, the real objects, true vectors, not coordinates, vectors. Now the good news is we know that the coordinates in the standard basis of any vector are the components of the vector, the entries of the vector. So we can kind of identify those. Okay, fine. And remember, in this case, the basis we are working with for R2 is the standard basis. So it's pretty much done. The job is done here. And again, reminder, the linear transformation was not defined by an expression. It was defined by its action on the basis vectors on the base of the basis B of R3. So that's just another way of stating the problem. Instead of just giving you an expression for the linear transformation, we just give you what the linear transformation does to a basis vectors from some basis of the domain. That's it. And then you have fun with it. So in this case, it's going to be super easy to build the representation matrix, because it's going to be representation matrix relative to the basis B of R3 and the standard basis for R2. Well, that's super easy now because we are already given the images of the basis vectors from basis B under the action of the linear transformation T. So they are here, tac, tac, tac. So these are the true vectors of R2, but they are also, their components are also their coordinates in the standard basis. So it's super easy. We just plug them into columns of the matrix, and this is our representation matrix of the linear transformation T relative to the basis B for inputs and standard basis for outputs. Super easy, straightforward. It was not costing us anything to do. So if I'm asked to find T of X, where X is some general vector of R3, using this representation matrix, that's the only thing I have. Well, the first thing will be to find the coordinates of the vector X in the basis B, because X is a vector in R3, so it's an object. This representation matrix here works on coordinates, not an object, on coordinates. And as input needs coordinates of X in basis B. So first thing I'm going to need to do is find the coordinates of X in basis B, and then multiply these two guys. As a result, I'm going to get the coordinates of the image in standard basis. That's beautiful. So first thing, find the coordinates of X in basis B. So how do we do it? Well, we need to find coefficients A, B, C from this equation here. So we just need to solve by Gauss-Jordan the linear system. So these are the basis vectors we were given. So basis vectors V1, V2, V3, and then this is our general vector in R3, X1, X2, X3, and we solve it. Once we solve it, well, we get this as a result. So these are the coordinates of the general vector x in basis B. So I just call it ABC for fun here. So knowing that, we have that by linearity, we can use linearity and get this. Very simple. Because you apply t to x, you are applying t to all this, and then by linearity you get this. But these people are given. TV1 is given, TV2 is given, TV3 is given. All I needed are the coordinates here. Finished. Another option is to use our, so both of them are good. I can use our representation matrix relative to basis B and S, and then multiply the coordinates of the vector x in basis B, and I get the coordinates of the image in the standard basis. Now we know that the coordinates of the image in the standard basis, it's equal to the image itself. So that's how we go around it. We need to use the representation matrix relative to basis B for inputs and S for outputs. So first thing I need to do is find the coordinates of vector x in basis B and then multiply these two guys. What I get are the coordinates in standard basis of the image. Ta-da! Of the image Tx. Super easy. So an example, if I just want to apply, I'm given this vector here, 2, negative 1, 4. And I want to find T of x using the representation matrix relative to basis B and S. Well, first thing is to find the coordinates of x in basis B. Well, we did the job, you just plug it and we find. So just plug it in, find, and then multiply these two, the matrix and the vector. What I get are the coordinates of the image Tx in the standard basis, but we know that's equal to the vector itself because we are talking about standard basis of vectors. Okay, so T of x, T of this guy, is 614. Pa-pam. Straightforward. Okay, so that was a direct approach. We could just plug the things in because we got the expression. So whichever way you choose it, do the product or just use the finalized solution, it's all okay. It's not a big deal, you get the same answer anyways. Let's make things a little bit more complicated for fun. I give you another vector, so a little bit different vector, and I'm just gonna show you a different approach which is equivalent, it's just as good as the previous one. So first thing is find the coordinates of this vector x in basis B, so we solve again with Gauss-Jordan the system, we find the coordinates, we multiply the matrix, the representation matrix with the coordinates, we get the coordinates of the image, all done, fine. So that's the classic one, that's no problem. Another way that is just as good, once we find the coordinates of x and b, so we found actually these coordinates, which means x is a linear combination of basis vectors v1, v2, v3 with these coefficients that come from the vector here. These are the coordinates in basis b of x. Then we can use the linearity, which is actually the same thing as if we use the representation matrix. Linearity, we apply t to the x. So we apply tx is t of all this. By linearity is equal to this. Straightforward. Now tv1 was given at the beginning. tv2 is given. tv3 is given. Just plug them. Tac, 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 tac. So you have your coefficients in front, tac, 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 and you get the same result. Which one you choose, it's up to you totally. It doesn't matter. You can, from here, by finding the coordinates, you can say x is equal to this linear combination of vectors v1, v2, v3. I apply the linear transformation t to both sides, and by linearity I get this. These people are given tv1, tv2, tv3, and I just plug everything into equation, I get it. Fine, perfect. Or you can say, well, I prefer doing matrix vector products, and okay, fine, just do it. Doesn't matter. Once you find the coordinates of x in basis B, and that's a must, there's no going around it, then you can do this matrix vector product or use the linearity of the linear transformation. It's up to you, all the same, same answer, equally correct, everything fine. Let's turn this a little bit spicier. So what if I'm given my representation matrix here relative to bases B and S, but look at this. I am given coordinates of vector x. I don't know what's the x, but I'm given its coordinates in a basis B2 of R3, not in basis B. So the vectors here are W1, W2, W3. So these three guys here. So they are not V1, V2, V3, they're different. And I say, hey, I know the coordinates of the vector x is a mysterious vector. I know its coordinates in basis B2, this ugly basis here, the new one. And I say, okay, now I would like you to compute T of x. Find me the value of the image of x. And you go, my God, how do I do that? You gave me I don't even know what's x. I just know the coordinates of x in basis B2, in this basis here with w's. And these are the coordinates. And you only gave me the representation matrix relative to the basis B. So the V1, V2, V3, and standard basis. Oh my God, how do I do this? I know that this matrix here multiplies the coordinates in basis B, but you gave me coordinates of a vector in basis B, two different bases. My God, what do I do? Well, instead of panicking, we could start thinking. So I don't know what's the vector x, but I can find it for sure, because you gave me the coordinates of x in basis B2, and you gave me the basis B2, the vectors W1, W2, W3, you gave me that. So by the definition of the basis and the coordinates actually in the basis, well, x is just a linear combination of W1, W2, W3, and these are the coefficients, 1, 3, and 2, pak, pak, pak. Well, I compute and I get this. So x is a vector 1, 11, 1. One part of the mystery solved. So I know what's the vector x. I just found it because you gave me the basis W1, W2, W3, and you gave me the coordinates of x in basis B2. Well, I'm just gonna apply the definition, not big deal. So I found the vector x, yeah. So now I have one part of the mystery solved. So I know what is the vector x. So now I need to find the coordinates of x in basis B, because my representation matrix works on basis B and S. So it needs coordinates in basis B for inputs. So I take the x that I just found and I find its coordinates in the basis B. How do I do that? Well, solved by Gauss-Jordan, the same system. So V1, V2, V3 slash the vector x, find the coordinates, solve, solve, solve. Here are the coordinates of the vector x in basis B. Yes, sir. So now we are almost there. I'm going to use these coordinates to multiply with the representation matrix. So now I have my representation matrix, multiply by the coordinates, and I get the coordinates of the image in the standard basis, which is equal to the vector. Wow. Another option, as we said, we could now, since we have the coordinates in basis B of x, we could just apply the linearity of, or apply t and apply the linearity of t. Well, whichever one you do, it's the same. It doesn't matter. At this stage, the game is over. Once you have the coordinates of x in basis B, you can either multiply by the representation matrix or apply the linear transformation t to the x on both, so on both sides of this equation, and then you'll have something like this, because TV1, TV2, TV3 are given already. So it's up to you which one you choose, it doesn't matter. I prefer multiplying by the matrix vector. It's just straightforward. No need to think too much. So you see, that's the beauty of all this. You can choose the way you want to compute the final part, but what you needed is to find the coordinates of the vector x in the basis B in order to use the representation matrix. because that representation matrix is relative to the basis B for inputs and standard basis for outputs. As we said, at the beginning, we were given just the coordinates of x in basis B2, some other basis. But we were smart enough to realize that we can use these coordinates and the definition of what they mean. It means that they are just coefficients in the linear combination here. So we multiply each of these with the corresponding basis vector from basis B2, and we got the vector x. We were smart to find that. So once we have x, now we need to find its coordinates in basis B. Once we get that, then we multiply the representation matrix Bs and the coordinates of x in basis B, babam, and we get the coordinates of the image in basis S, standard basis, and we know that the vector is equal to its coordinates in the standard basis. So that's easy. So that's it. It's pretty straightforward, even though at the beginning it looked very scary and we didn't know what to do. But if you take things step by step using the definition and the common sense, things are just not so complicated and quite easy actually. Just pay attention and go step by step.